Okay, so welcome back. On this third part of the introductory lecture, we're going to discuss a little bit more about Bayesian networks, and I'm going to see all the probabilistic graphical methods that we're going to cover during this course. So I'm going to have a just overview of what are those methods, and you probably will recognize most of them, or will learn about them in the remaining of this course. So. All right, so we get to a point that we have the structure of this Bayesian network, this graph represented in some way. So we identify the most important variables. We identify the causality between them. So we connect them using an edge. And this edge is connected, so it has a direction indicating what is the direction of the influence. It's going from one variable to the other. As we have this, and I mentioned to you that there is not a single Bayesian network. You may ask why this one is the correct one. I read the description of the problem and I had a different idea. Okay, that is fine. We are modeling. And when we do the modeling, we realize that there are many different ways of solving the same problem. And we needed to incorporate into the model as many details as we can, but we also have a compromise with efficiency. And it is interesting to note that as we add more edges to this structure and make the graph more dense, it will be more inefficient, both in terms of size and also in terms of inference. So our objective here is not to state every possible influence that one variable can have in the other variable, but we want to make the graph as sparse as possible. We will model only the direct influences, so only the direct causes, and we'll let the flow of influence go through the graph, and other variables will indirectly influence the other by this sequence of steps that we have a path in the graph and we will have a chain of influence. So even though we are just modeling, for instance, the direct influence between Q4 here and E, Q4 will also influence A indirectly, right? By influence E, and E influence R, and R influence the variable A. So there will be a chain of influence in the graph. So we will try to make it as sparse as possible, only modeling the direct influence and let the indirect ones to be paths in our graph. But all that information is a sort of qualitative type of information. We are just mentioning who influences who the indirect way, but we are not saying how much is this influence, how strong it is, right? And there is the part that the probabilities come into play. We will quantify the power of the influence, right? So how strong is the influence using probabilities. The idea here is that for every node, there will be a probability table inside the node, but that information will be local, in the sense that this node will have a probability table that only has information about the variable in the node itself, plus the parent nodes. No other variable will be expressed in this probability table, right? So for every node, we will have the influence quantified in terms of the table that includes the node itself and its parents. So we can look at a few examples here. So for instance, we may have a node that has no parent. So this is one example, the clerical error. So the variable C, the probability that is associated to that node is this one. And we are saying that in this example, the variables are only binary, so they are only true or false. We are saying that the probability of having a clerical error, that is the professor entered the incorrect grade in the system, is very small. It's 0.001. So because it was said in the description of the problem that the professor is very careful. So that's good. As C has no parent, the only information that we have in the table is C, not any other variable. Some other variables have one parent. So one example is here, the Jack. Right? It has one parent, and the parent is Q4. So in this case, we have a table like this. It is a conditional table. You're going to express what is the probability of J for each possible value of Q4. So you enter that information. You see, it's local. It says that Jack will confirm that we have the correct answer, given that we have the correct answer. So Q4 is going to be true, is 0.99. So Jack knows the content of the material very well. So if we both got it correctly, so the probability of always having the Q4 correct is very high, right? And we can see that as in the case of the first table, the table for C, we are compacting the representations between, because we have just two possible values, true or false. So we are expressing the value for true in the case of the table C. For false, it's going to be the complement, 1 minus, and we can figure it out. So here we should have 4 values, and here we should have 8 values because we have 3 variables. So again, we can feel that we are providing local information. We did not touch that idea of having the full joint probability distribution with all variables. Even though we have 1, 2, 3, 4, 5, 6, 7, 8 variables, we are not expressing that table that has 2 elevated to 8 power possible values. And it's going to be a lot easier to understand, right? So if we have to express just the probability of the clerical error, it's simple to figure out. The same way the probability of jacking confirming the answer is correct, given that our question is also correct, is sort of simple to figure out. So these probabilities are much easier to understand, to express, to collect, to get it from data, or get it from an expert, than if we have the full joint distribution table. That is the trick here. So what we are doing is what we are factorizing. So we are expressing this full distribution with a smaller distribution, smaller tables. And each table, if the nodes here have a small number of parents, each table will be small too. So it will be efficient. So that is the central idea of using those graphical models. Great. And something that is also important that I was forgetting to mention is that every query that we want to make, we can make the query use an algorithm that gives us the answer, right? So we are not expressing certain probabilities here. So we are not expressing, for instance, the probability of the Q4 given that we have observed in A, because there is no direct connection between Q4 and A. So there is no direct edge between them. So we never express that probability. But can we compute that? Yes, we can. The way to compute that is using the inference algorithm that are going to build on top of the representation. Something that is very important here is that even though we are not representing the full joint probability table, we can compute that full joint probability table from this Bayesian network. Yeah? As far as we specify the probabilities, the probability tables for each node, and we have it specified for all of them, so we can see the figure here that we just specified for the C, for the Q4, and for the E, right? So we have it specified just for a few of them, but we need to specify for every node in the Bayesian network. Once we have done that, we can compute the full joint. We don't do that because the full joint will be very expensive. But if we do it, it is very interesting. The full joint will be unique. That is, what I mean is that there will be a single value for each row of the full joint distribution, right? And so if we ask the same question again and again, so we ask this question for the second time, the answer will be the same, right? So it's a compact representation, but it will not confuse us, right? So it will not give different answers when we pose the same query. It will always give the same answer. So there will be one value for each possible combination of all variables that we have. So for each entry, each row of the full joint distribution, there will be a value that's guaranteed, and this value will be unique. And that is very good, right? Okay, and the final notes here is that this table is what we call the deterministic conditional probability table, because it only has values zeros and ones, right? And the interpretation here is very simple. It's that we will only earn an A if we have a Q3 correct, a Q3 graded, and a Q4 correct. So that is expressed in this line. All other possibilities will be zero. Actually, well, there will be more ones here as we extend this, because we are just representing 4 values, but actually this table has 8 possible values. But the central idea here is that we only earn an A if we have these 2 conditions true. And this is a deterministic table. It all occurs in probabilistic modeling. Awesome. So what are the techniques for modeling, right? So how we create a model from a problem. And there are 3 main ways of doing that. One way is very similar to what people use it to do when they want to create the first expert systems. There was a process of interviewing an expert, asking questions, and try to figure out what will be the model for the knowledge that the expert has in his mind. So we call it elicitation. That is the process of asking the questions, understand what are the model, what is the reasoning process of the expert, and try to encode that into a representation that in our case is going to be a graphical model. A second possibility is from the problem specification by itself. Some problems, as we read the specification, it clears what is the underlying graph that you need to use. Maybe a very simple example for that is when you want to model an image as a probabilistic graphical model. In that case, we use undirected graphs, and a very common way of representing this is using a grid like this, much larger than this actually, where each node is going to be a pixel, and we want to model the influence that one pixel has in its neighboring pixels. Right? So the graph comes naturally when you are dealing with image, comes naturally from the structure of the image, let's say that way. The third one is closer to what we used to do in machine learning. And in this case, we learn the probabilities and possibly also the graph from data. You can imagine that if we have data, we can learn the probabilities by counting, right? So it's going to be frequencies of the variables occurring in the data, but it's a little bit less clear how you do with the structure. But that's not very difficult. Actually, the structure comes from the dependency between the variables. So we will check which variables are dependent of each others and try to build the graph. So we have these 2 ways of doing. Actually, these 3 ways of doing. Actually, when we are working with this machine learning approach, we can learn just the data. So we can complement these methods by using a combination of them. So we can elicitate the structure by talking with an expert and learn the probabilities that we call the parameters from data. But we can also learn the structure from data and the parameters from data. So we can make different combinations of this. But it's important to know that if we have the structure, we can learn the parameters from data. If we don't have the structure, we can learn the structure from data too. So we can compose this as we wish. When we are learning from data, there are 2 different ways of doing that. One is what we call the maximum likelihood approach. We're going to detail this more during the course. And the second one is the Bayesian approach. So now things start to get a little bit confusing, because you say, okay, it's a Bayesian network, and what is the Bayesian approach? Bayesian have different meanings depending on the context that you're using that. In this specific context here, we are talking about an approach that uses a likelihood and a prior. So it will impose a prior over the networks. It is a slightly different approach, more towards what we call the Bayesian statistics. So it is very common in this approach. So during the course, most of the time we're going to use this maximum likelihood. That is the most common one, but we will have a dedicated lecture to touch about the Bayesian approach for learning Bayesian networks. Great. So once we have built the network, we have the structure, we have the probabilities, it came from somewhere, from an expert or from data, we can start to ask questions. And this is the process of reasoning, right? One important thing is that the Bayesian network will give a unique probability for each proposition. So if we ask the same questions again and again, the answer is exactly the same. And it will give one probability for each possible combination. So it's going to be sound and complete, right? So it will be always the same answer, and we'll give an answer for any query that we ask, any possible combination of values that we ask. There are a few types of questions that we can ask. I will not get into detail right now. I'll just give you a few examples. We will detail what are the different types of queries that we can make. We call it probabilistic queries in a future class. But there are marginal, there are conditionals, there are a few possibilities that we can ask. There are map ones. I will not get into detail now. Notice that for those questions, we have not entered that probability directly in any tables here. And we are asking questions about a single node, or maybe about two nodes that are not directly connected. So we have to go through a process of inference. One example is this one. What is the probability of drill earning A grade? And we're just asking a question about this node here in the middle. We don't have it, right? If we look at its probability table, what we have is the conditional of E given Q3 and Q4. So we don't have the probability of E being true, so we have to compute that. Okay? So we call this the marginal query. There is also a possibility of conditioning the query to something that we have observed. It's a sort of a what-if scenario. So what if the probability of this, given that I know something else? And this can be expressed in this form here. So what is the probability of Q3 being false? So in this case, the Q3 was not graded, so it's wrong here in the slide. It was not graded because Q3 is false. And E is also false, and the drill did not earn an A. And another query that we can express is like this one. What is the probability of Q4 being true, given that E is true? Is the probability that Jack will obtain the same answer as drill on Q4, given that drill earned an A? So we are looking at different things here, relationships between the nodes. They are not directly connected, and the process of inference will calculate this for us and give us an answer. It's very important that if the representation is compact, the algorithm will be efficient, and the time that we will get the answer will be feasible. All right, so we are getting towards the end of this introductory lecture. I just want to show you a few probabilistic graphical models that I'm going to study during this course. In this table here, we have separated the graphical models according to three different dimensions. One is if the graph is directed or undirected. The second one, if the graph is dynamic or static. And the third one, if it is a probabilistic graphical model or a decisional graphical model. So by now you should be more or less familiar with all those ideas, but we can have directed or undirected graphs. These are the two main families of graphs, and I'm going to study them. We have dynamic static, something new for you, but if you have a static graph, it will be the same for the entire time. If you have it dynamic, as the time passes, we can create new nodes and remove other nodes, so the structure can grow or reduce with time. So there will be dynamic. And probabilistic or decisional is exactly what you are imagining now. So there are some probabilistic graphical models that give us a probability as an answer. The decisional ones will take the probability plus some other information and will compute the utility function that will give us an utility, and they use the utility to make a decision. So these are the possibilities. So we have here the Bayesian networks. So it's directed, it is static, and it's a probabilistic graphical model. We have a variation of the dynamic of the Bayesian networks. They are the dynamic Bayesian networks. These are Bayesian networks that we can add nodes as time passes, and so it will change in terms of structure. We have what we call the Bayesian classifiers. We have a class that's going to touch those methods, but you can imagine Bayesian classifier like naive Bayes. It's a very simple sort of a Bayesian network, and it also directed, static, and probabilistic. These methods here, like the Markov chains and the hidden Markov models, these are dynamic methods. They also change with time. The Markov chains are very simple. It's just a chain, it's just a sequence of nodes, and we are interested in understanding what's going to be the final distribution. That's how the distribution changes with time, and it's going to converge to a final distribution. The hidden Markov models is a little bit more common to see, and it's going to be a chain of two sequence of nodes. One that's hidden to us, you're going to ask questions about those nodes, and the one that we can observe. We have the Markov random fields. There are undirected graphs, also static, very common in image processing. And here we have three different decisional probabilistic decisional graph models. They are the influence diagrams, the Markov decision process, and the partially observed Markov decision process. Okay, so we have an overview of probabilistic graphical models. I hope that now you have a little bit more understanding what you're going to study during this course. Again, I think this area is very interesting because it's a joint research of statistics, where we get the probabilistic reasoning, and computer science when we bring the graphs, and we put those two components together in order to have something that can use probabilistic inference in a larger scale with a larger number of variables. I will invite you to take a look on chapter 1 of the Archie book, where he covers this introductory part, and you can find a little bit more details there. See you.